Hello, everyone. This is the first course of Introduction to Graph Theory. So, yeah. Today I will introduce what graphs are and then what topics that we will learn throughout this semester. So, let's start with this famous puzzle. So there was this city called Königsberg. In 18th century, there was a famous puzzle regarding this city. In this city, we have this like islands, and then this land. And then there was this bridge between them. There are 7 bridges. And then one day, some guy asked whether you can start from one where, and then cross each bridge exactly once, and then complete the journey. So in this case, I failed because this one is not visited. And then as I have already visited all other bridges, there is no way for me to like move from here to somehow either A or B, A or D, and then cross this without crossing the same bridge twice. So there was this famous puzzle, and then it was solved by Euler that this is not possible. And how Euler dealt with this question, the first step that he dealt with is to remove the irrelevant information. So there are many redundant information in this picture. For example, the shape of this land A is not relevant to this problem. Even if we make it differently look like, make the shape of island different, it's still the same problem. And for example, the length of these bridges or the width of this bridge is also irrelevant to the problem. Even if this bridge becomes thinner, as long as you can cross it, it's not too thin to cross it, then it's also irrelevant. And then whether this bridge is made of stone or wood are not relevant. So by getting rid of all those irrelevant information, you are only left with all those essential information. And there are, of course, more than one way to, express this this essential information. How the Euler did is using these dots and lines. And he gave the name of this ABCD to this lens. And only thing matter is that there are these 4 objects, A, B, C, D. So using the minimal information, we write down that as a dot. So all the shape of those lands are gone. And whether that land is filled with buildings or not, those are also gone. It's just the object. We represent them as dots containing minimal information. And again, this bridge, we also lose all the irrelevant information. The only thing that we care is whether this bridge is connecting which land to the which land. So in here, which dot to which dot. So we can represent that as using this line, or more correctly, curve. Then we have this picture. And then this picture contains all the essential information to the problem, and then not much more irrelevant information. Of course, you can draw these lines in this way or this way or this way. Geometrically they are different, but we can pretend that they are the same line. We only care about this line or curve is representing that there is a connection between these two. This is some sort of simplification or abstractifying or abstractifying, abstractification. I don't know whether that's a correct English word. And this kind of abstractifying or simplifying occurs a lot in other situations as well. For example, if we have say, we have to go somewhere using metro, and then there are many metro stops, and then we need to figure out how to get from point A to point B. And we have A and B, and we want to get there. And then while you're doing that, I mean, there are other stations, and then we can take a line 1 or line 2. And those problem, in solving those problem, the irrelevant information, if we just get rid of all the irrelevant information, then we again get the picture like this, which are the metro map, which simply again use dots or circle to denote its stop, and then draw this line or curve to denote the connection between them. Additionally, they use like colors to represent whether this is line 1 or line 2. But it's more or less this kind of picture with a few additional essential information. Also, like road map, when you have to go drive from somewhere to the other, you use this navigation, and it tells you to how to go there. But what this navigation actually do is it has a map saved inside, and those map is also more or less this kind of a picture with more complicated information. And also in like social media, say, in social media, I mean, you are friends with someone, and those can be also represented using this kind of picture. Its users are that, and then there is like this connection between them or non-connection between them. Based on that, social media recommends you to friends with someone or suggest you some, I mean, things based on those information. So this shows that it's kind of a recurring theme to make this kind of a simplification of the problem. And the result is somewhat like this picture. So this gives the motivation to define this concept. So we want to give some name to this kind of picture, which contains essential minimal information regarding this kind of problem. And that name is graph. So again, this is an introduction to graph theory. So we are studying about graph. And then we need to understand what graphs are. And then I'm saying that this is graph. Of course, I didn't give you any explanation. I didn't give you any mathematical definition. But by giving you several examples, you already have some intuition on what graphs are. There are some objects, and there are some connection between them, and then you want to study them. So graphs are, what are graphs? Graphs are, I mean, roughly on our intuition, this is graph. It's like a picture. There are dots and then lines between them. But it's not really a picture, but more of a collection of information which are relevant to this information, these problems. Then what are those information? Those informations are the connection between objects. So this is more of a graph is a collection of binary relation. between objects. So connections that I mentioned are connecting between two objects or two dots or two stops or two places or two users. So connections are binary relation. It's between two objects. And the graphs here are collection of information, and where information is this connection, which is a binary relations. So graphs are this, a collection of binary relations between objects. And we will learn about this. And what do we learn about this? So in order to know, in order to choose what topics we need to learn about graph, we have to look at the problems that we are interested in. If we are interested in this kind of problem, then we need to develop the tools to solve them. That introduces interesting topics on graphs. That's very natural, right? So we need to see what problems do we care. So as we have seen in the metro map problem or this bridge crossing problem, one obvious usage of graph is this connectivity or connection. Let's say connectivity. So as in the previous example of bridges or metro map, our goal here is like moving. So we are on the graph and we are moving on this graph to achieve certain goal. In the bridge crossing, we want to move. So we are here, then we move along these lines from one dot to the other. And again, in metro map, we are at one point and we move along this line to get to the some point, which is our goal. So in this problem, these graphs are networks, and we want to either move or transport something. So that our goal is met. Usually that goal is to getting somewhere, to reach somewhere. So this will naturally define what connectivity is. And then considering some various situations, we will be able to define concepts which are relevant and more complicated than just connectivity. And then we will study about them. And another problem, which are also natural, is matching problem. So we can again consider many situations. We might want to solve, say, low birth rate problem, which is very, imminent problem in this country. What do we have to do? We have to match the couples. So there are people here. And then we want to match the couple so that they are like a good couple. They like each other. Then we can encode those information that if these two people are, fond of each other, so that they can form a couple, and we add an edge. We add this line between the dots, and here dots represent the people. And then we want to provide efficient matching. Whatever this efficient means, that's depending on the problem and how you define this problem. But that's one situation that we want to provide this kind of matching. We didn't really define what matchings are, but intuitively you already get it. And also we might want to deal with, say, other problem like high unemployment problem. In that situation, there are jobs and then there are like people who want to work on the job. And then we want to assign jobs to each people, which is called hiring. So we might put like job 1, job 2, and so on. So these are jobs, and there are candidates who want to work on the jobs, people. And some person is qualified for this job, have certain license or certain background or certain knowledge, but might not be eligible for the capable of the job 2, but job 3 is okay, and so on. So this provides, again, the graph, the picture that we mentioned. Then here, assigning job to each person is what? Finding this matching between job and people. So this is also an important and useful concept studying this kind of problems. So we will learn about this. And also there is another concept which is called coloring. So what did we do in the matching problem? We want to match the dots so that they form good couple, good matching, right? Here, the two matched one has to be good each other. Either they like each other, or either this person is good at the job, and then job is well done by the people. But there are other inverse situations. There are people, there are like dots which we want to avoid. So we want to avoid conflict. For example, there could be many people, and we want to assign group. So these are group 1, group 2, and group 3. But if two people does not like each other, we want to avoid putting them in the same group. That's one such situation. Or, if we want to more technical situation, there are like a tower, like cell tower, and we want to build a cellular network so that here we have a satellite. And then, like, if someone uses some like cell phone, then it's transmitting to this cell tower and then go to the satellite, and then transmitting to another cell tower and then go to the person you are calling. So this is cellular network. And then while doing each bell tower, they use some certain frequency. So they use certain frequency channel, like from 100 to say 200 hertz. And here, like 300 to 500 hertz. They use different band of frequency. But if these two bell tower again use the same band of frequency, then if someone call here using this frequency band, it might, I mean, it might get, okay, let me correct myself. Instead of that, if they use the same frequency channel, they might interfere. So if something is transmitted using that frequency channel, then it's supposed to be picked up on one cell tower, but the other cell tower's communication can be hindered by this. So what do we want to do? If they are close each other, then we want to assign the different frequency channel. And here, what do we do? There are people, and then you assign group number to each people so that the same group number people can work together as a group. Here you have many cell tower. We want to assign the frequency band so that the cell tower with the same frequency bands are far apart. So we assign certain label to each object here. Then we consider that as a coloring of graph. So this can be represented as graph. So dots are the people who all cell tower, and then the lines between them are the pair of people who does not like each other, or pair of cell tower which are close. And assigning group number is like coloring these dots. Group 1, group 2, group 3, so that the ones connected by the line have the different color. So this arises the problem on graph coloring. How many colors do we need to color the dots so that the connected dots have the different color? So we will learn about these concepts and other concepts as well. So we will explore these concepts, and then while doing that, we also naturally introduce other concepts as well. And once these many concepts arise, it's natural to study the interactions between them, how they are dependent on each other. If we understand one, can we understand another? And we will prove theorems about those relations between these concepts. And while doing that, we also use the other mathematical concepts. Mathematical concepts that we have learned in other courses, which seems to be not relevant to the graphs at first glance, but we will use them to prove things about graph. This provides connection between graph theory and other branches of mathematics. For example, we will learn about some statements in topological graph theory. We all know the famous four-color theorem. So we have a map. There are like countries here and here, here. Can we, color the map so that each country is filled with one color. And if two countries share the border, then we want to use the different color on those two countries. How many colors do we need? The answer is four colors. And again, this can be considered as a graph problem. Roughly, in each country, you put these dots. And then when they share a border, we add a line between them. Then we get this graph. And then now this is a coloring problem on this specific graph. So that all the pairs that's connected by the line getting different color, whether that's possible or not. And here, but in order to answer this question, whether we can use the four colors to complete this graph coloring, we need to learn about properties of this graph. Those graphs coming from a map. So that's not all graph. Not all graphs come from a map. There are certain graphs that come from a map. For example, it's not difficult to check that if you have a 5 dots and all pairs connected, this will never come from any map. So that kind of ask us to study about drawing graphs on a surface. When certain surface, or in this case plane, is given, can we draw this graph on there so that each this dot is actually dot in that surface, and then this line is actually curved there. And then what topological property can we get about this graph? That's related here. So this provides the connection between topology and graph theory. Yeah, we will learn about this later. And also, we will see connection between probability and graph theory. Usually how probability arises is that we want to find the construction that satisfy certain good property. Usually what we do is we come up with certain ingenious idea to make such a construction, but oftentimes it's useful to find the construction in a not ingenious way, not creative way. For example, we just take a coin and then we just flip coin to decide whether we want to draw a line between two dots or not. That will give you a graph, and then that could, we can compute the probability that that resulting graph satisfies certain good property. Of course, that give you a probabilistic distribution, not just one graph, but oftentimes that is very useful in studying graphs. And we will see how we use those probabilistic tools to solve the problems in graph theory. And also, there are certain connections between graph theory and linear algebra. Again, recall that the graph is just a collection of binary relation, and this is one way to represent such an information or express such a collection of informations in a succinct way so that we can our intuition can grasp it very immediately. But of course, there are other ways. So one of the other very natural way is using metrics. So you have these columns and then rows, and then we assign objects there. So we assign objects in this column and rows, and in each entry we put either 0 or 1 in here. representing that 0 means that there are no connection between these two, and then 1 means that there are connection between these two. Then we get this matrix, and then this matrix again contains the same essential information we need to encode in the graph. Recall that in the Koenigsberg bridge problem, all we cared about is the information about the connection between the objects, and as in the many other cases. So this matrix also contains the same essential information. And we already learned how to deal with the matrix in linear algebra. And by studying this matrix in terms of many linear algebraic concepts, some surprising connection between linear algebra and graph theory also arise. We will also take a look at those aspects. So that's what we will do in this semester. And in next video, we will define some basic concepts and notation, which will be helpful for us to study graphs throughout the semester.